Hey guys, so my name is Annika, and today I'm covering Chapter 11 of Holt Physics, which is Vibrations and Waves. This chapter is going to be broken down into 4 segments. First, we'll look at simple harmonic motion, then we'll measure simple harmonic motion, finally we'll move on to properties of waves, and then wave interactions. So we're going to start in this video with section 11.1, which covers simple harmonic motion. The main part of this segment is going to be Hooke's law, but before we can really look at that, I'm going to introduce periodic motion. Periodic motion describes objects that swing back and forth along the same path. So if you visualize a pendulum, like I've drawn here on the left, or a swing, you can see that these two objects pass back and forth through the same path, following the same pattern over and over again. The same is true for a mass on a spring, as I've drawn on the far right. This mass will move back and forth based on the force of the spring. That's what Hooke's law is really going to lead us to study. Here are some basics for spring motion. A spring is at equilibrium point, as I've drawn here, when it's at its relaxed length, or the length it would have naturally without any external forces. When a mass is on the spring and it reaches equilibrium point, the velocity reaches its maximum. However, because the spring is at a relaxed point, it exerts no force, so we say F is 0, and therefore acceleration is also 0. There are 2 other extreme positions on the spring that the mass can occupy. The first is the maximum compression. This is when the spring is as far condensed or compressed as it's going to be within the mass's pattern of motion. The other is the maximum stretch. This is when the spring has been stretched as far as it can possibly go, and the mass is about to be released from that stretch point. At these positions, the velocity is 0. However, because the spring is under so much stress, the force is at a maximum, and therefore the mass's acceleration also reaches a maximum. And it's important to note that in the real world, a spring set in motion in this way would eventually slow and then stop because of friction. But in the situations we're studying, we're going to make sort of ideal situations in which it oscillates indefinitely, and we can study the motion of the mass. So with this information in mind about springs, this is Hooke's law. It states that F, or the elastic force of the spring, will be equal to negative kx. Now we can look more closely at what these variables mean. The negative sign suggests that F, so the force, and x, the displacement, have opposite directions. So you just need that to switch the directions of the two. The spring constant is something we've gone over before when we were studying work and energy. It's measured in newtons per meter, and it's basically how much force is required to stretch the spring a certain distance. Finally, we have x, which is the displacement. This is the distance of the mass from the spring's equilibrium point, or its relaxed position. And just to note, when a mass is on a spring, this entire system becomes an example of simple harmonic motion. Simple harmonic motion is defined as periodic motion as a result of a restoring force that is proportional to displacement. So as you can see, that makes sense because here we have a force and a displacement that are proportional to one another. And in this case, the elastic potential of the stretched or compressed spring will provide that restoring force that it needs for the motion. The concept of periodic motion can also be implied when we're looking at a simple pendulum. This also has periodic motion, just like the mass on the spring, because the pendulum is moving back and forth on the same path. However, in this case, the restoring force comes from gravitational potential. In other words, it's a component of the bob's weight. As you can see over on the left, I've drawn this pendulum with a bob on a string, and we have these 2 forces on a bob. We have mg, or the force of gravity, the bob's weight, and then we have tension, which is pulling up on the string. Now, if I were to draw the 2 components of the bob's weight using these axes, as you can see, there's this x component that would point in and kind of pull the pendulum along its path of motion. That's the restoring force that keeps it in simple harmonic motion. You might wonder what happens to the pendulum when it reaches this lowest point. At this point, the gravitational potential is all pointed downward because that's the only component of the pendulum's gravity. However, in this case, momentum is what keeps the pendulum moving. You'll remember from previous chapters that momentum must always be conserved. So in this case, because the pendulum starts off with initial momentum, it has to keep moving even through its lowest point. So here are some practice problems for section 11.1. Number 1. A slingshot consists of 2 rubber bands. If it takes 32 newtons of force to stretch the bands 1.2 centimeters, what is the spring constant of the bands? So in this case, we're looking for K, which we know is measured in newtons per meter. So we basically want to find how much force is required to stretch the bands 1 meter. We have 1.2 centimeters and 32 newtons, so put the newtons on top, that's 32, and then 1.2 centimeters needs to be converted to meters, that's 0.012 meters. If we do this division, we get that K is equal to about 2,667 newtons per meter. That's how much force is required to stretch the rubber bands. Number 2. How much force is required to pull a spring 3 centimeters from its equilibrium position if the spring constant is 2,700 newtons per meter? So now we're starting to use Hooke's law. We see force is equal to negative kx, and then since this problem is just asking how much force, or the magnitude of the force, we can sort of disregard this negative sign because we're just looking for magnitude rather than magnitude and direction. So with that in mind, we're looking for force. We have K, which is 2,700, and then we have 3 centimeters, that would be 0.03 meters. I multiply these together and get 81 newtons of force.